While we are recording this, everyone is going to be on mute. If you have any questions throughout or afterwards, please feel free to use that chat box or the questions panel, and we can answer those questions for you. If we run out of time, we can always answer those through email afterwards, but we'll have some time to answer some questions today. Okay, like I said, we are recording the presentation. After everything is completed, we're going to send you a survey through your email, and there will be a link to the recording on that as well. All right, so let's get started. Today's presenter is Evan Zabowski. Evan is the Senior Technical Advisor at Test Oil. He is a certified lubrication specialist with extensive experience training tradesmen and professionals in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. Evan is heavily involved with STLE. He's been a member for over 18 years and has served the last 8 years as editor of TLT magazine. He recently joined the board of directors, and he previously served as the editor of the Basic Handbook of Lubrication, the 3rd edition. So Evan, if you're ready, let's get started.
Great, thank you, Ashley. So for today's presentation on grease fundamentals and analysis, I've broken it into 3 sections. We have a reasonably lengthy section on basic properties, a somewhat shorter section on performance properties, and then we'll finish up with a brief section on interpretation of in-service grease analysis. So to begin, let's dive into the basic properties. Now, before we get too far into any basic properties, we should always start with a couple definitions to make sure we know what we're talking about. So one of the most commonly used definitions for grease is one straight from NLGI that's been reproduced in ASTM, and it simply describes grease as a lubricant that could be anywhere from a solid to a semi-fluid, and it describes it as having a thickener. Now some trivia for you. The word grease is from an old French word for fat, graisse, which is based on the Latin word crassus, and that's often out as extra information. But I prefer a different definition. This one the Volds wrote over 60 years ago, and I've highlighted a few key parts here to their definition because you can see it's quite a long one. But when they described grease as a lubricant, they gave it some properties, and they said it has to remain in contact, it can't leak out or be squeezed out, and it must stand up to mechanical shear at all temperatures, and of course be able to flow from one spot to another. And of course this is largely a bearing application. Now this definition expands upon the simple one given by NLGI and sort of gives us an idea of the performance of the grease as a lubricant. Now, at the end of the definition, it does say this is an exacting set of rheological requirements. Now, not everyone is familiar with rheology, so let's quickly define that as well. Rheology, as you can see, is the science of deformation and flow of materials. Now, when we talk about solid materials and they deform, we usually refer to them as being elastic when they will revert back to their original shape. When we talk about fluids and their deformation, we usually refer to them as being viscous. And when we have a liquid that deforms and doesn't return to its original shape, it's not elastic, it is definitely viscous, right? It will not revert. Now, greases, on the other hand, are actually called viscoelastics because, well, they're a little bit of both. They can deform permanently, but they also have some elasticity to them, and it is these rheological properties that we take advantage of in using grease as a lubricant. So in the overall functionality of grease, we know greases are thick when they're at rest. When they're not moving, they don't flow, they don't tend to puddle, they tend to sit. But once we mechanically shear them, they will begin to thin, so we describe these as shear thinning lubricants. And the easiest way to picture this is to picture a grease as being composed of a thickener and an oil. The thickener is kind of like the sponge that holds it all together. The oil is the lubricant that wants to lubricate the moving parts. So when we mechanically stress a grease, it's kind of like squeezing a sponge and getting the oil to come out. But as you know, with a sponge is reasonably elastic and it will absorb back what you've squeezed out of it. So that's kind of the basic premise of what a grease boils down to fundamentally. Now when we think of greases, the overall composition of a grease is largely a lubricating oil. There's a significant portion of thickener and a very small portion of additives in most greases. Now obviously, because oil is the largest component, that should be a key focus area for some folks. They usually want to know what kind of oils go into making a grease. And that's a pretty easy question to answer because pretty much any oil could end up as the base oil lubricant for a grease. Now, one of the most important properties of a lubricant, as we are well aware when we deal with liquid lubricants, is viscosity. So a common question is, what viscosity of these oils do we use in greases? And that really is dependent on the application. So I've got this table here that outlines some overall viscosity ranges depending on the application. So you can see the higher the speed and the lower the load, the thinner the lubricant will be. So this is not atypical to how we would select an oil as a lubricant. Greases largely follow the sort of the same pattern, and we will have obviously thicker greases when we have slower speeds or higher loads. Now the next portion of a grease is the thickener. And when we think of the thickener, like I said, think like a sponge. It is a fibrous entity. It is holding on to, trapping, if you will, the lubricant. But the thickener does impart some properties to the grease. Now, in no particular order, one of the properties that it affects is the texture. Now, this is not just the appearance, how it feels. It is how tenacious or tacky or adhesive, whatever word you want to use, the grease can be. It helps define how well it will transfer from one moving part to another, how well it will flow. Things like this are sort of covered by the texture characteristic. One of the other ones is dropping point, which largely relates to the upper operating temperature limit, or at least helps define the upper operating temperature limit. We'll also deal with a bit of the shear stability, how well the grease will stand up to mechanical work, if its consistency will change or if it will remain close to new grease values. We have water resistance as well in some of our greases. Definitely there's some natural water resistance and some natural effects that may occur. So we sometimes will select completely different thickeners for a wet application than we would for a dry application. Lastly, we have pumpability, how well the grease will move. This is a greater concern when we start dealing with long runs or cold temperatures or both. Now, the thickeners that we use basically fall into two very, very broad categories. We refer to them as soaps and non-soaps. Now, with a soap, I always joke that they basically end with EM, lithium, calcium, sodium, barium. And to keep the pattern alive, you'd pronounce it aluminium, but of course most of us just pronounce it aluminum. But the non-soaps tend to be the clays, or they're sometimes referred to as the bentonites and the polyureas. Now in our world here in North America, the non-soaps are not terribly popular. This chart here from NLGI outlines the most common greases, clearly are lithium-based greases, occupying about 2/3 of the North American production. And you see it's kind of split into two categories, conventional and complex, which I'll get to on the next slide here. But when you look at the other non-soaps, that's only 1%, and the clays are 4%, and the polyureas are 6%. So that's not much of the, or at least North American market. We predominantly use lithium. If not lithium, we tend to lean towards the calciums and aluminums. Now, getting to the difference between a conventional, or what a lot of folks call simple, and a complex, this is the quickest explanation I can give you. A simple grease is one where we prepare it by reacting with a single organic acid, and a complex is one where we create it by reacting at least two organic acids. Now in there, we often have the primary soap, and then there's a complexing agent. Now this complexing agent will enhance some of the grease properties, and the one that it most enhances, or how people view what complexing most enhances, is the dropping point. So to cover that, let's look at the dropping point test briefly here. The dropping point test is a test where we heat a small portion of the grease and we see at what temperature we will get a drop of oil to extract. This is considered to be when the thickener starts to fail, right? When the sponge isn't holding on to the oil anymore. A rough rule of thumb, some folks will subtract 50 degrees Celsius from the dropping point and call that the upper operating temperature limit. But on the next chart, I'll show you some very broad numbers that help define what the upper operating temperature limit is compared to dropping point. But I just want to stress, like I said, that this is the test most affected via the complexing agent or via a complex grease. So taking a quick peek at this chart, what I'm hoping will stand out is that any of the greases that are listed as being a complex will have the highest dropping points compared to any of the other variants of the same soap-based greases. And if you scroll over to the right-hand side of the table, you will see the maximum operating temperatures, and you will note that there is a greater than 50-degree difference between the dropping point and the maximum service temperature. So that rule of thumb doesn't necessarily hold very true. So I would always, of course, refer back to the product data sheet for knowing what is the recommended maximum service temperature for any particular greases. Like I said, this table here is just some broad-based ones to help illustrate that complexing definitely enhances the grease's dropping point significantly. The rest of the chart just shows you how shear stable these greases are naturally and if there's any water resistance to them, which most of them do. It's only sodium that really stands out as not having decent water resistance. But between dropping point, there is one other test that we should be well aware of in terms of basic properties of a grease. That is the penetration test. The penetration test is where we take a volume of grease and place it in a cup. Over top of the cup we have a weighted cone, which you can see on the right-hand picture. That weighted cone is released from a set height and it drops to the grease, and then we wait 5 seconds. Once the 5 seconds is over, we measure how far did that cone penetrate into the grease. Because we're using a pointed cone and we're dropping it, a lot of people will sometimes mistakenly refer to this test as the dropping point test. But it is not. It is the penetration test, properly termed, and it is the test that we use to define the NLGI consistency grade. So when we do that, the test that we're performing is on a sample of grease that has been worked, meaning that we have a paddle with some holes in it, and we work the paddle through the grease 60 strokes, and that gives us a worked grease sample, a sample that has undergone some shearing. Taking the worked penetration, we can get the NLGI consistency. If we were to test it on unworked grease, what we're doing there typically is contrasting the two measurements, seeing how much the consistency changes after working. So it gives us an idea of how shear stable a grease might be if we look at the unworked and the worked results together. But sticking with the worked results in the NLGI grease consistency, it's only fair to define those as well. This here lists all the NLGI consistency numbers. They start at 000 and go all the way up to 6 as a grease goes from soft to hard. The measurements are in the next column over. Those are in tenths of a millimeter, and most people don't get terribly concerned with dealing with the numbers. But the last two columns just illustrate sort of an analogistic approach to what these greases might look like. Smack in the middle is a NLGI2. This is the most common grease used here in North America. That's what we consider to be the normal grease, and it has the consistency of about peanut butter. Anything lower than 2 is going to be a bit thinner, less thick, and anything higher than 2 is definitely going to start to feel harder and harder and flow less and less on its own. That's just a quick reference table just to help illustrate where we are in the world of greases. Commonly speaking, like I said, in North America, we use NLGI2s. Sometimes we use NLGI1s. The only time we tend to go towards the aughts and double aughts and triple aughts would be if we're dealing with outdoor applications where the temperatures are expected to be colder, or if we're dealing with centralized grease systems and we need good flow characteristics because we have long runs or maybe multiple runs in a large area. Where we tend to use the harder greases is very limited applications. I've come across them being used on cables for ski lifts, but other than that, you don't see them terribly often. Now, one of the things about the NLGI consistency number is it does appear in other forms. One of the classic ones would be DIN 51502. This is a way of coding greases with a set of letters and numbers. So I've given you the breakdown here just in case you've come across these as a grease specification. The example I'm using here is a KP2K minus 30. The first K refers to basically the application of the grease, what kind of grease it should be. The second letter tells us a little bit about how it's made up. The third one, the 2 though, that is the NLGI consistency number. So this is an NLGI2 grease. The second K happens to refer to how well it reacts with water. You'll see that in the coming slide. And then the very last one is a maximum or minimum, I guess would be the better way of phrasing it, service temperature. So we get quite a bit of information out of that if you know how to break that down. So I've broken down the first K on this slide. You can see what P stands for. On this slide, basically it just describes the type of base materials going into the grease, what kind of lubricant we're using, and may refer to some of the additives. The 2 obviously was the NLGI2. The next K, like I said, that had everything to do with how well it reacts with water. So this gives us a reaction and an upper operating temperature just broadly. And like I said, the last number refers to minimum service temperatures. So we do come across NLGI numbering when we read specifications. It's often on the packaging for the greases. It helps guide us as to what consistency the grease is. But dropping point and consistency only tell us so much about the grease. There's quite a few other properties that we'll take a quick breeze through so we have an idea of what else is out there in terms of specifications on the grease before we put it into use. So let's get into these performance properties here. Now, performance properties are driven at this point by the additives as well. So different additives can be put into the grease to impart or enhance some of these properties. So giving you a quick rundown of the properties and types of additives that we're looking to modify, we've got a couple slides here. So first off, we've got structure modifiers. This helps change the structure of the grease. It may help with some of the flow or tackiness characteristics. We've got antioxidants, or what are sometimes called oxidation inhibitors. It's one and the same. But these are the ones that try and minimize the reactions with oxygen and any catalyzing with water contamination getting in there. So they do help prolong the life of the grease, prevent it from degrading, and they do help with some of the rust and corrosion protection as well. Now, for wear protection, greases kind of use 2 different types of additives. The first one listed here is the extreme pressure additive. Extreme pressure additives do help in high temperature, high pressure applications. They're predominantly used when we're greasing gears, more so ever than you would find in a bearing type application. When we're dealing with bearings, we tend to stick to anti-wear agents, and these ones don't necessarily need the pressure to create the sacrificial coating that they do. They're reacting mostly based on temperature. So it's kind of a small difference, but it helps define when they become active and where they're most needed. We also have anti-rust or metal deactivators that are, of course, there to help the surface from reacting with oxygen and water. So they don't do much to help the grease prolong its life, but they will help the components from oxidizing and corroding. We also have viscosity modifiers. These are there to help prevent the lubricant from thinning as much as it would normally do at the higher temperatures. So this gives us an improved VI of the lubricant itself. And all of these additives tend to be quite common in most greases. Where we start to see some application-dependent ones are in things like pour point depressants, where we might use those for expecting the grease to work in outdoor and cold temperatures. We can use emulsifiers and demulsifiers to change the characteristics of how the grease will interact with water. In some cases, we want to make sure that the water is pushed out, dropped out immediately. In other cases, we'd rather it mix with the grease and be driven off due to higher temperatures somewhere within the lubricated system. We also have tackiness agents that help in terms of giving the grease some tack. So if we've got particularly slow speed and open applications, we want to make sure the grease doesn't just run off and lead us to a under-lubricated asset. And of course, we've got solid additives and friction modifiers there to help maintain fluid friction films and give the a lubricant a chance to separate the moving parts. Like I said, every one here is listed as an application-dependent one. You wouldn't necessarily expect to find them in all greases. You may or may not find one or more of these in greases you are using. Now, the testing that we use to help give us an idea if the grease is performing in the way we want are covered by many different tests. So the first one I'll describe to you is the oil separation test. The oil separation test is one where you place grease in a little mesh basket and you measure by percent weight how much oil separates from the original grease after 24 hours and 25 Celsius environment. What this helps is it does correlate directly with how much the oil will separate out in 35-pound pails of grease. So this is useful for people who are concerned about storage of grease, shelf life of grease, what's going to happen. So you can take this simple result and correlate it. Now this tends to be reported on product data sheets. This is not, as I'm going to describe all of these are not typically done on used or in-service greases. These are all for new grease selection. EP properties can be measured a number of different ways. One of the more common ways is by this method here, which often gets referred to as the 4-ball method or the 4-ball weld. It's a test where we take 3 steel balls and place a 4th ball on top of it. We rotate the ball on top and we keep increasing the load, how much force it's pushing down on the lower 3 balls, until such time as welding occurs. We report the lowest weight at which no welding occurs as the EP weight for this test. Now, one variant to this test is done with the same 3 balls, same 4th ball on top, but in this case it's done under set condition and you report the scars on the lower 3 balls. So this method is also referred to as the 4-ball method because it does employ the 4 balls, but most people try and differentiate it by calling it the 4-ball scar or the 4-ball wear. So don't confuse these two tests. One is basically a maximum load before scoring. The one that we've got on screen right now is how much scoring under a set load. So always try and compare apples to apples when we're doing these measurements. One will be reported typically in kilograms. The other one, the one we're looking at right now, will be reported in millimeters. Now, another way that some people try to measure the anti-wear or EP characteristics of the grease is by using this particular test apparatus. This one is commonly referred to as the Timken test or the Timken EP test. And it also reports a maximum load where there's no scoring. But rather than using a 4-ball setup, what is up in the top of that apparatus, kind of where it's black on top, is a rotating spindle that you push a block against. Now this test is a very reasonable test. It helps us define basically how well the greases will stand up under EP conditions. But sadly, a lot of folks have taken a simplified version of this test apparatus, mostly meaning they take something that's got the spinning spindle and a block with a lever to help produce force on that block. and they'll run this around in trade shows, and they'll call it something like a lubricity test. And most oils do not perform well in this particular test rig, or even the condensed version of this test rig, unless they have been treated with an EP additive. So just kind of food for thought, that if you ever see something that's similar to this one, looks like basically everything sitting on top of the bench, not the entire bench with it, make sure you know this test is meant for defining or characterizing EP characteristics and not for any other property of a lubricant. So it should be used on greases and or gear oils. It shouldn't be used on any other products. So if somebody's trying to sell you an engine oil or a hydraulic fluid and doing a demonstration with this, they're pulling your leg. But it is a legitimate test rig. It does have a legitimate ASTM method behind it, and like I said, most people refer to this one as the Timken, as they were the ones who developed it. Now, one of the other characteristics we like to know about a grease is how well it prevents corrosion. So there is a set test for this that stores a bearing under a humid condition for 48 hours. It is a specific bearing, so it's got varying metallurgy between the outer ring, the inner ring, the bearing cage, and the rollers. If there is one 1 millimeter dot on any of the components, this test is a fail. So it does make it a bit difficult to compare two failing greases, because you have no idea the severity of the failure, whether one failed from one single dot and the other one failed due to complete coverage. But if it passed, it means there are no dots greater than 1 millimeter. So a passing result can be viewed as a good grease. A failing result is a bit subjective. You don't have enough information to really pit one against another one. Further, with our humid conditions, there is a water washout test, which is again a very set bearing that has been loaded with grease. You spray it with water directly into the bearing for an hour. At the end of the test, you measure how much weight was washed out of the bearing. It can be done at two different temperatures, so if you're comparing results, please make sure you're comparing tests done at the same temperature. It's the only way that the playing field is level there. If your grease application isn't necessarily a bearing, the other variant to a water test is the water spray-off test, where we just measure how much by weight, again, is sprayed off of a surface. This is a much briefer test, though. It only takes a few minutes to get the results from this one. Now, one of the other performance property tests that doesn't belong to ASTM but is often reported is a US Steel DM43 mobility test. This test characterizes what is the flow rate in grams per minute at 150 psi. So you need to be aware of what temperature it's run at, and make sure again that you're comparing apples to apples, or at least reasonable apples to apples, that you're not looking at results that are 20 or 30 degrees apart. Temperature-wise, you want to make sure they're at least similar temperatures if you're trying to determine the flow characteristics or how mobile the grease will remain in colder temperatures. This test is largely only a concern when people are speccing a grease for a centralized grease system, and again, it's like I said earlier, it's when you have long runs, that's when mobility tends to be an issue. One of the less common tests, but you will still see this one on product data sheets, is the roll stability test. And this is just another variation of seeing how much consistency will change after being worked. In this case, it's not being worked with a paddle being mashed through it like the penetration test does. This one's actually a shaft basically sitting inside of a very loose bearing. It's just a hollow cylinder, but it works the grease in a single direction. So this helps identify if there's any directional changes in the consistency from the grease before the test and after the test. It's kind of how this. Now, one of the very common questions that we get when it comes to grease testing is when people have gone through perhaps some of these tests here in terms of the product data sheet results. At the end of their selection process, they ask themselves, but is this compatible with what I'm already using? Thankfully, ASTM comes to our rescue one last time here in terms of performance tests, and there is a grease compatibility test. Now this ASTM method actually measures several different properties, and some of the key things it's looking for is that there's no significant decrease in the dropping point of the mix, that the mechanical stability stays within range, so once you've got a mixture and you work it, it doesn't change dramatically, and also the consistency doesn't change significantly after some heating. They want to make sure that there's not an incompatibility of the thickener chemistries and that you're not causing the lubricant to drop out or the viscosity, or sorry, the consistency of the grease to change. And these are done at different mixtures. You know, typically they're done at 10-90, 50-50, and 90-10% mixtures. Sometimes they're done at 25-75 and 75-25 as well. But this gives you a broad spectrum, and of course you have 100% of each grease measured as baseline references on either side of the compatibility testing. So there's quite a bit involved with grease compatibility testing. Definitely urge folks who've got this question in the back of their minds to involve their lubricant supplier. They have already done this testing on the grease in question, or they at least may be able to, or may be willing to foot the bill so that you're not stuck paying for all this testing if it is their grease they want to sell you. But moving along, now that we've talked about the basic properties, the performance properties, let's talk about what do we actually test once we've put the grease in service. So in this section I'll describe the simple tests that are done and some basic interpretation tips just to try and prevent you from falling into the common pitfalls. Now, the foremost test that we run on service greases is elemental spectroscopy. So let me explain elemental spectroscopy to the uninitiated. If you're familiar with this, you've probably seen it on an oil analysis report, but still let me explain the concepts here. So how we measure a sample via what we tend to call SPEC, or IC for short, is by diluting a sample and injecting it into a plasma. Now, once we put the sample into the plasma, it is ionized. For lack of a better word, think of it as burning. The temperature of this plasma is nearly 10,000 degrees Kelvin, which is hotter than the surface of the sun. So pretty much anything that goes into here, whether it be liquid or solid, it's going to burn, or more correctly, it will ionize. Now, when we ionize a sample, what happens is a bunch of light is given off. As you're well aware of, setting anything on fire produces light. What we measure is the intensity and the wavelengths of these lights, because every element on the periodic table will emit a unique color spectrum. And if we know which spectrums to look for and we measure the intensity at those spectrums, we can tell you how much of any given metal, additive, or contaminant is present in the grease sample. Now, this test is reported in parts per million, and I try and urge people to understand what a part per million is. So my simple analogy is it's more than just thinking of it as 1 in a million. To really picture what 1 in a million looks like, think of it this way. Imagine if you purchased some kind of raffle ticket for $1 million cash prize, and you win, and you go to collect your $1 million cash prize, and they have you collected over at a treasury. The treasury, when they go to give you your prize, is trying to promote the use of $1 coins. So they pay you in $1 coins. To make matters worse, they don't pay you in rolled coins, they pay you in loose coins. So they hand you a giant sack of 1 million $1 coins. Now, if you're dragging that sack back to your vehicle to try and get it into the trunk, and that bag happens to catch on the trunk release mechanism or something like that, and the bag tears just a little, and that one single coin rolls out of the bag and rolls right underneath the middle of your vehicle. A lot of people look at the 1 in a million with this analogy and say, would I go after that $1? If I've got nearly 1 million in my trunk and there's one that got loose, do I care? Well, of course, you know, some people always jokingly say they do, but by and large, most of us be willing to let one go because, in 1 million, what's one? But imagine after you pull away, a homeless person walks by and they see the same dollar on the street. Would they go after it? Well, probably, of course they would. And a lot of people then think, well, when you've got nothing, one is significant. But the truth of the matter is, whether you had 1,000,000 to start with and one gets away from you, or you've got nothing to start with and you come across one, it's still the same 1 in a million. It's still just that $1. So when you look at these results being measured in parts per million, understand they're 1 out of 1,000,000 always. So when a result goes from 1 to 2 parts per million, a lot of people will say, doubled, that's significant. But would you say the same thing if it went from 11 to 12, or if it went from 101 to 102, or if it went from 1,001 to 1,002? It's the same change. It's the same part per million. So try and think of it more that way than the winning a raffle analogy. It's not very significant what 1 part per million is most of the time. We tend to look for major changes in these values. So like I said, I like to dwell on this part per million aspect just for a couple minutes to make sure we're really interpreting these numbers properly. Too often people get sensitive to small changes in the numbers because as a percentage they may be high, but still it's ultimately the same amount of material at the end of the day. So something we should know about this test. Because we are trying to ionize the sample directly into this plasma, the particulate in the sample that will ionize completely tends to be in the 0 to 5 micron range for size. Between 5 and 10 microns, the accuracy starts to drop off, and pretty much around 10 microns, this instrument becomes blind to what's there. So what this is driving at is if the particulate in your sample, whether it's contaminants or wear metals, whatever, is larger than 10 microns, it will not appear in these test results. Now, as I've got listed in the subnote here, wear particles that are generated under normal wear conditions will definitely be under 5 microns. Wear particles that are generated by severe conditions, where we've got insufficient lubrication or contamination or misalignments or whatever it might be, those will start to be outside of that range, and therefore they will not show up here. So you might be lulled into a false sense of security that your system's looking good. So keep that in mind. As well, normal airborne contaminants will appear in the 0 to 5 micron range, will be measured, but gross contamination, like when we've got just tons of dirt getting near this, again, this stuff can go largely undetected by this test. So as such, we always recommend, when this is suspect, that we follow up with something like the ferrous wear concentration or analytical ferrography. These tests will cover the large particles. So there's always a handoff here. I just want you to be aware of that as well. The last thing I need you to be aware of is that even though we're talking about submicron type additives being present in greases, which of course fall well within the 0 to 5 micron range of analysis, the other fundamental thing we need to know about this test is that it only identifies the elements. It doesn't identify chemicals, compounds, alloys. This test will never tell you you have brass wear. It will tell you you have copper, lead, tin, and zinc wear, which from there you can derive that you have brass wear, but it doesn't say you have brass. As such as well, it doesn't tell us that you have an EP additive. It doesn't tell us that we have an AW additive. It tells us we've got phosphorus, or we've got phosphorus and zinc. That's as much as it can tell us. So we have to intuit the rest on our own. So understand that when we're measuring additives, we're seeing the parts of the additive, the pieces that make up the additive. So it's possible in some of these grease samples, the additive may be depleting, may be deteriorating, degrading, whatever word you want to use, but it's still there. And as long as it's there, it's measured and shows up on the report. So try not to take a steady value as an indication that all things are good. It may still be a degradation process occurring, so keep this in mind. And that's why we say when it comes to interpreting the elemental spectroscopy results, trending is your most important aspect. If you look at this report here and start at the top and work your way down, you're going to find when you get to phosphorus and zinc that the samples do not appear to be measuring up to the new grease values. We see that back in February of 2014, they were maybe half of the values that they should have been. But by this latest sample in May of 2015, we see a significant decrease. What I want you to be aware of, though, is this isn't suggesting that the anti-wear additive is going away or that it's depleting or that anything bad is happening to it. If we keep reading the report, we will see what probably is a better reason for those results decreasing. If you look down at the lithium and sodium values, you will notice that they are the highest in the used samples, but they are not present in the new grease sample. The new grease sample has silicon present. So the new grease sample says it should have been a silicon-based grease. The sample from February 2014 suggests that it was a sodium-based grease, or possibly with some silicon contamination in there from the original grease. But by May of 2015, we don't even have the sodium present anymore, and we've just about depleted all the silicon. This is suggesting to us we've got a mixture of greases going on here, and somebody is adding in a lithium-based grease. Well, there may be compatibility issues just between the thickeners, but the big thing is that probably explains why the anti-wear isn't there. They're not using an anti-wear additized grease anymore. So when you look at results, trend them. Try and see what the trends are and look for all the correlations. Don't just dwell in any one area and try and make a determination from there. It's very common that greases get mixed or the incorrect grease gets added at certain points in time, and this will definitely affect the results. So try and treat that in with your interpretation. Now, one of the other tests that we do is we do measure for water contamination, because water contamination doesn't bode well for most greases. It can just outright displace the grease, which water is a poor lubricant. You'll get a sudden increase in wear. It can obviously cause corrosion or pitting of parts, so you will see some wear metal increases, possibly from a water increase. But you might not always see it, depending on how much the water is actually causing corrosion or wear and how severe that is. It's very possible that you'll see the water long in advance to any wear or corrosion, and that when you do see the corrosion or the wear, it may not be in that normal elemental spectroscopy range. You might only see it in, say, the analytical ferrography or the ferrous wear contamination. So we should always look at that ferrous wear contamination as well. Now, we do need to understand this test is not limited to size, so that means it may or may not correlate with a spectroscopic iron, but it is only measuring ferrous, meaning iron components. So this will have definitely no correlation to any other wear metal report. But whether or not it correlates with iron is still telling. If we see that the ferrous wear itself is low, but iron is high, then most of the wear is going to be in the small category, in that less than 10 or in that 0 to 5 range. So this is probably normal wear. We don't get too excited about those kind of results. If we see it the other way around, where the ferrous wear concentration is increasing, but we don't see much of a change or any change in the spectroscopic iron, then we know this wear is likely to be more severe. It's going to be all larger than 10 microns. If both of them go up together, though, definitely we have an abnormal wear mechanism occurring, and we should follow up with analytical ferrography. Now, analytical ferrography is a bit of a forensic test. Let me see if I can simplify and give you a quick explanation of how it's done. If you look at the picture there, you'll notice the oil flows from the right to the left. That slide is actually on an incline. It is highest on the right-hand end and it is lowest on the left-hand end. Underneath that slide, it is a glass slide, there are a series of magnets. When we flow the oil or grease sample down that slide, by fluid dynamics, the particles will settle out from largest at the top on the right-hand side to smallest at the bottom on the left-hand side. The magnets underneath will separate the ferrous from the non-ferrous. So what we typically find is that we get smooth tiger stripes when we see a lot of normal wear particles, a lot of really small wear particles. If we see random spotting, looks more like a cheetah, I always joke that's the wrong kind of cat, and that indicates abnormal wear. So we do expect to see wear particles. We are looking to see what kind of wear particles we have. So this slide is analyzed under the microscope at the room temperature which it was created at. but then it is done 3 further times under various levels of heat treatment. And under heat treating, some of these metals will melt or discolor, which helps reveal to us what alloys they might be. So when we do an analytical photography, this is the most forensic test you're ever going to get. It will help identify all the particles seen on the slide by their shape, which helps tell us what kind of wear mechanism might have caused them to be there, by their composition, so we'll know what type of alloys they are, if they're low carbon steel, high carbon steel, brass alloys, whatever it might be, what size they are, which helps tell us about the severity, and the surface condition, right? Was this created by rubbing wear, corrosive wear, things like this? So with all these classifications, we can really identify just how severe or abnormal the wear might be. Now, to give you an idea of what one of those reports would look like, this is the one section of the report where it does break down, as you can see going down the list, a bunch of different types of wear, and then a bunch of different types of particles. So some of those particles, like dark metallic oxides, those tend to be from welding, when surfaces come into such severe pressure that they will temporarily weld themselves to each other, and then when they pull away, the little spall that is created in that mechanism is very dark metallic oxide. Red oxides, on the other hand, is just a fancy way of saying rust. But the rest of them tend to be fairly self-explanatory. What's causing them to be there, you can see we categorize if it's relevant, what size they are, and we'll tell you what the metallic composition might be. So in this particular example, we do see we've got a fair amount of ferrous wear. Most of it is large, so that would indicate some abnormality. In terms of severity, you can see that these have largely been identified as heavy in terms of how much particulate we're seeing on the slide. So this is a pretty bad looking sample. Now, one of the things is that people then try to correlate this back to that spectroscopic metals, and they may or may not find the correlation. But again, look at the particle sizes. What we're seeing here may in fact be much larger than what the spectrometric analysis will detail, so you might not always see a correlation. Particularly when people see a lot of contaminants, when they see dust and dirt listed, they'll look for the silicon value, and you may not find that correlation is there. So one of the other things that's started to help round out the whole report and give you a pretty detailed view of what's going on are some pictures. Now understand these pictures are under heavy magnification, so they're not seeing the entire slide that was created. They're close-up views of areas of interest, so they may not be representative of everything you've just seen in the previous table. Right? We try and identify something that is curious to us that will help guide you as to just how bad or where this problem is originating from. So again, make sure that you don't view these pictures and say, wait a minute, why isn't this correlating with the verbiage? Why isn't the photography correlating with the WPC? Why isn't the WPC correlating with the spectrometric? The reason we do so many different tests is because we're seeing it from so many different angles. And so if they could correlate so close and directly, we wouldn't need to do them. So I always caution people from trying to correlate the results too closely, trying to see that they should all match up. That's not how they work, and you wouldn't want them to work that way, because that would mean you're paying for tests you don't need. So some tips to wrap up here. Knowing that grease samples inherently are very difficult to collect in a truly representative fashion, you should make sure that you, of course, take whatever steps possible to get good samples. And lots of our customers, instead of just trying to scrape it off into a bottle, have gone the way of grease thief and similar sampling mechanisms, and we get much samples there. But as long as you try and take a sample from a consistent location, in a consistent manner, in a consistent timing, we can get a pretty reasonable idea what's going on there, as long as we don't dwell too much on the absolute values. So as I say, trending is the most valuable tool. Try not to worry too much about what the actual numbers are, especially when you're comparing one system to another. Look at the trend. If it's not increasing, it's probably not a problem. And if it is increasing, regardless of how low the results are, it's probably indicating a greater problem than a sample that's stable with higher values. Now, if you do see high-level contamination, but you don't see any wear metals with this, oftentimes that simply means to us it was a bad sample. Somebody scraped, leaking purged grease from the exterior of the asset, which is often, of course, still quite tacky. Outside contamination is stuck to it. Therefore, there's a lot of contamination and it doesn't correspond to any wear. So when we see that, we don't tend to think it's a very good sample, because the more contaminated the grease is, the more wear should be being generated. So like I said, make sure you try and take those samples as consistently as possible, meaning consistent location, consistent method, consistent interval. That will give you the best stab at trending your results and seeing any significant changes and helping identify if you have a contamination issue, if you have a wear issue, if the greases are beginning to break down, anything like that. So with that, I still have about 9 minutes for questions, so I will pause at this point in time and turn it back over to Ashley and see if she's gotten any questions via the chat.
All right, thank you, Evan. There have been a few questions, so let's go over those. And again, if anybody else has any questions, please feel free to use that chat feature. Okay, the first question that we have is, someone's wanting to know if there's a faster test than ferrography for analyzing the bigger chunks of metal.
Well, I can kind of answer that question with two sides to it. One is ferrography doesn't take as long as you might think. This is where I can wave the test oil flag high above my head and tell you that we do all ferrography tests same day. So there's no delay in requesting a ferrography or triggering a ferrography on any one test. But if you were looking for a different approach, one of the other things we offer, which is far less forensic but is nice and quick, is X-ray fluorescence. XRF, as we call it for short, is basically a similar version to elemental spectroscopy that is not limited to particle size. We can analyze liquid and solid samples with this, and you will get still an elemental concentration, not a compounds or alloys type approach that ferrography will give. So it is faster, but it is less, right? You're not getting quite the depth of analysis. All right, what's one of the other questions?
Okay, somebody else is asking what would be a quick method for determining if more than one grease has been used?
That's a pretty common fault that we find. The fastest way to determine that without getting deep into your pocketbook is similar to the example I covered by looking at the elemental spectroscopy and looking at the thickeners. Generally speaking, like I said, lithium is the most common thickener that we use in North America. So if you're mixing two lithium greases together, you're not going to see much of a change in the lithium content. So then you're going to steer your attention towards the additives, looking for phosphorus and zinc, any molybdenum, things like this. That's kind of your quickest way of seeing if there is a definitive mixture of greases, provided, of course, nothing obvious is standing out like a significant color change or that. But if you need more than that, we can obviously do more testing, but it does begin to take quite a bit more time if we're trying to differentiate greases, especially when people want to find out what the other grease is. That definitely gets tricky, and that may not be an easy question to answer. But in short, like I said, look at your spectrometric analysis. That covers bases quite well for the most common mixtures of greases. Right, another question?
Okay, I have one here. What does NLGI stand for?
National Lubricating Grease Institute. They're the governing body for a lot of the specification on greases. So they define the consistency. They also have a classification system as an example for automotive greases, defining whether they're chassis greases, wheel bearing greases, or multi-purpose greases. But that's who NLGI is.
Okay, I have a couple questions here about sample amounts and sample volumes for each test. Can you just quickly go over how much would be needed?
For everything I just described there to you, the spectrometric, water content, wear particle classification, or ferrous wear concentration, sorry, and the ferrography, generally speaking, if you can fill a 5 ml syringe, 5 grams of sample, that is enough for us to be able to do that testing. If you can give us more, it helps us if there's any need for a rerun, and helps make sure we can get as representative of a sample as possible. But we're not requiring large volumes of grease here. Most of our customers tend to send in a syringe or two from each sample point. That more often than not is enough sample for the routine testing and still has some left over for any additional testing that may be required. It's worth noting that some folks like to confirm some of those performance tests. I will caution you that almost every performance test I listed requires a very significant volume of grease. The penetration test, as an example, requires 1.1 pounds of grease to do a single test. There's quarter and half versions of that, so take a quarter or half of 1.1 pounds, and that tells you how much we would need if you wanted a proper ASTM consistency value. If you're willing to deal with consistency determined rheologically, then we can still work with the 5-gram samples, more than enough. And any other questions?
Okay, I have one here. Is there any incompatibility if you mix a non-soap grease with a soap base?
Funnily enough, if you look up grease compatibility charts, which tend to be created per manufacturer, meaning that they largely represent their greases mixed with their own greases, not crossing different manufacturers, the short answer to most grease compatibility questions is no, they're not compatible. By and large, compatibility seems to be always at a loss, that when you mix any two greases, they tend not to mix very well, tend to have some negative synergies occurring. I don't know if I could make any blanket statement, soaps versus non-soaps, but the broadest brush I can paint with is, generally speaking, most greases are not compatible with most greases. If you do have concerns specifically, like I said, I wouldn't rely simply on a grease compatibility chart because most of them don't agree with each other. I would actually request compatibility testing from the lubricant supplier, and more times than not they might already have done this or have some close idea. You're not necessarily going to be out of pocket or waiting a long time for that answer, but if they haven't come across your particular application, definitely you should send it out for testing rather than try and just go with, like I said, some kind of blanket statement that says, yeah, they're probably okay. Because, like I said, my experience tells me more times than not there's issues that occur. Any other questions?
I have one more here. What frequency is recommended for grease sampling and analysis?
Well, that largely depends on the severity and criticality of the application. Some customers will do monthly, some will do quarterly. Obviously, there are certain applications that are difficult to procure the samples, so that tends to decrease the sampling interval. But when you start to see that it's very, very critical how the grease is performing, the effort usually gets made. So I kind of recommend as a minimum that you start with quarterly and differentiate from there if you can get away with less frequent testing. I've seen, as an example, when I deal with power plants, that on their cooling tower applications, they will just test those once a year because they're difficult to procure and they tend to be very reliable. When we deal with the wind turbine applications, we start to see that even quarterly may not be often enough, and they will attempt to get monthly samples. So it can go to either extreme from quarterly, but quarterly is a good starting point. If you still have failures after taking quarterly samples and you need to increase it to monthly, if after a year or two of collecting data you see your systems are relatively stable, maybe you can back off from quarterly to semi-annually. All right, any other questions?
There are a few more questions, but I think some of those will be best answered through an email.
Okay, and we're at our time anyways. I don't want to keep anyone on the line longer than we promised.
All right. Well, thank you very much, Evan, for presenting that information. And like I said at the beginning, an email survey will be coming out shortly, and there'll also be a link to the recording on that email. So look for that. All right.
All right.
Thank you very
Thank
much
you.
for attending, and have a great day.